All right, now that we have some background information about just what polar coordinates look like, as well as how to graph their functions, and we're aware of some of what the basic graphs look like, at this point now we're going to start actually doing things like taking derivatives. So to start with the idea of derivative, let's just think about dy dx. Now clearly dy dx is in the rectangular coordinate system, and it is okay for us to find and to want that dy dx. That's going to be the slope of the tangent line at any point on those polar curves, right? Which is exactly what it meant in our rectangular system. The fact that we're looking at a polar graph isn't a big deal because we can convert back and forth between rectangular and polar. We did that in our first lesson on polar coordinates. And even when we looked at those graphs, like maybe for instance the cardioid, there is an equivalent rectangular equation, just it's a lot easier to write something like y equals 2 plus 2 cosine theta than r equals, than the rectangular counterpart. But when we find a point and the tangent line, the slope, we can still express that dy dx. But if we have a polar equation, like maybe that cardioid that I have written there, we have r expressed as some function of theta. Whoops, not theta prime, of theta. That means in order to get the traditional derivative, we're not going to need to think of it in terms of dy d theta, dx d theta, right? Because then the thetas can cancel out. And we did that same kind of process with our parametric derivatives. And it's not going to be a big deal to get the derivative of y with respect to theta and x with respect to theta, because we know the polar conversions for those. For instance, I know that x, to get an x component, it's r times cosine theta. Written in terms of my function, that would be f of theta cosine theta. I also know that to find the corresponding y rectangular coordinate, it's the radius times sine theta. And since that r is typically a function, I will also write it this way. All right, well, now let's find the derivative. That means I'm going to take the derivative of y. I'll take this expression of y and find its derivative. You'd have to apply the chain rule. So f prime theta times sine theta plus f of theta cosine theta. And then I will find the derivative of my x with respect to theta, again applying the chain rule. Now, because the derivative of cosine is negative sine, I'm going to go ahead and change my sign here. My sign in front of sine. So even though it all turns out the same, kind of what happens in people's brains tends to differ. Some people like to think of this simply in terms of like a formula to memorize. And if that's something that you like to do, then you'll probably even think of it in terms of r. If I'm doing these a lot, finding these derivatives a lot, I tend to kind of think of it in terms of the formula. But if you don't find these frequently and, don't have the formula memorized, or if you're just doing different things with derivatives, a lot of times for me, I find it easier just to know, okay, I know how to find x, I know how to find y, let me work with those conversions and with what will then become the derivative. So you can take either approach. And I'll do some of both as we go through the examples. Even with the AP questions, at least for me, I find that sometimes one approach or the other is easier depending upon how the question is written. Let me kind of explain what I mean by that a little bit. So find the slope of this polar equation, r equals 3 minus 2 cosine theta at the point 2 pi over 4. So that's a radius of 2 and a theta of pi over 4. If this were an AP question, it'd probably be a multiple choice type of question, and I would probably maybe think of it in terms of the formula. So I would find the derivative of my function of r, which would be, let's see, the 3 will go away, cosine will be a negative sign, which will make it positive. So the derivative of r is 2 sine theta. And then I can write the derivative dy dx. So r prime, which is 2 sine theta, multiply it by sine. I'm just looking at the formula above. Plus r, and r is 3 minus 2 cosine theta. Got to multiply that by cosine. Then in the denominator, 2 sine theta for r prime times cosine. Minus the r again, but times sine. Now, I guess since it's asking me to evaluate, you could go ahead and just make the substitution for theta. Or you could simplify it a little bit first. I mean, that's entirely up to you, right? No big deal. Whatever you think is easiest. I think I'll at least do this distributing. So distributing allows me to see a little more easily that there are going to be like terms. So maybe I'll at least combine that when I evaluate it. So this is going to be at pi over 4. And pi over 4 on the unit circle, that's the easy one, right? Radical 2 over 2. And since those are like terms, I'm going to write that as 4, and then I can say radical 2 over 2 squared, since it's the same for sine and cosine. All right, so I have some values canceling in the numerator. In the denominator, let's see, I'll have a 4 that can cancel and a 2 squared. Or radical 2 squared, so that's 2, and then minus 3 radical 2 over 2. Suppose I need to get a common denominator here and multiply by the reciprocal. So the 2's cancel. 3 radical 2, 4 minus 3 radical 2, and I'll stop there. I don't know what version of this answer they're wanting, but I kind of like the way that looks, so I'm going to let that be my value. If you recall with the parametric equations, we looked at horizontal and vertical points of tangency, and we're going to do the same thing for polar. Let's start with horizontal point of tangency, meaning that our slope is 0, which would happen when dy d theta is 0. So if you have the formula memorized, you could look at the numerator. Again, I tend to forget that formula, but I don't forget how to create or to convert to x and y, which is r times cosine. Oh, times, so as I say that and then I make a mistake, y is times sine. I think I will go ahead and distribute this before I take my derivative. That's just my preference. Okay, now I'll get dy d theta. Derivative sine is cosine. Apply the chain rule. Let's see, I'll do the cosine first and get a negative sine squared plus cosine squared. And I need that derivative of y with respect to theta set equal to 0. Now, if I'm going to solve this, it's not good that I have both sines and cosines in the equation. I'm going to have to use a trig substitution. And it'd probably be best to make it all in terms of cosine. So there's my Pythagorean substitution. Let's get ready to factor this. And so let's see, what are our factors? 2 cosine theta minus 1, cosine theta plus 1. Yep. So I need to know when cosine is equal to 1/2 and cosine equal to -1. Cosine is 1/2, a couple places on the unit circle at pi over 3 in quadrant 1, as well as in quadrant 4, so 5 pi over 3. And cosine is -1 at pi. Now it did say to find the points. Right now I've only found theta. So to express that as points, I will need to come up here and substitute that in for r, or into theta to find r. All right, so what happens at pi over 3? Well, I get 1/2, right? We just kind of are doing this backwards. So that would be 1.5 pi over 3, as well as 1.5, 5 pi over 3. I know that pi is -1, so that will yield a 0 pi. So I have 3 points of horizontal tangency. This is kind of long, I realize this, but in the end, there's a point I need to make. So I have to go through this and find the vertical points of tangency. Slope is undefined, so dx d theta needs to equal 0. R, which is 1 plus cosine theta, times cosine theta. That's what I tried to do earlier, huh? All right, well, my derivative. Derivative cosine, negative sine. And then, let's see, plus 2 cosine theta, negative sine theta. I just need to change that to a negative. And let's see, this is going to be a little easier to solve. I think I'll factor out a negative sine theta. So I'm looking to see where theta sine is equal to 0 and where cosine is equal to a -1/2. Well, sine of 0 is 0 in pi. Cosine equal to -1/2, just our other pi over 3 answers, right? The 2 pi over 3 and the 4 pi over 3. We need those expressed as points. Well, I can't draw my arrow, but we're going to R again. I guess I need to go this way. Going back to R. And notice that we're going to get some of the same answers. So when I substitute in like 0 or pi, I would get 0 pi again. When I substitute in the 0, I skipped that one, sorry. I would get 1, so that would be 2, 0. The 2 pi over 3, so I'll be minusing 1/2, so I'll have 1/2, 2 pi over 3, and 1/2, 4 pi over 3. Okay, so the whole reason that I went through this tedious process, and I probably bored you with that, is because it's important that we realize that we're getting this answer twice, and it can't be both. So what it ends up doing is eliminating it from both. And I think maybe an explanation of that will be helpful if we think about the graph. The graph of this is a cardioid. Again, you don't have to have all these memorized, but let me maybe sketch it here to the side. It'll be something like this. I like making it look a little more like a heart than it actually does. All right, and where are these points at? Well, if we think about the horizontal points of tangency, 1.5 pi over 3 is probably right here. 1.5, 5 pi over 3 must be down here. Let's go to the vertical points of tangency that we know. The 2, 0, well, that would be this one here. The 1/2, 2 pi over 3, and 4 pi over 3, that's here at the edge. This will end up being kind of the same vertical lines. So the one that's indeterminate, the one at 0 pi, let's see, is there another color I can use? Let's just use this, is right here. Because we could draw a vertical line or a horizontal line, and kind of think of like absolute value graphs, right? When it was a little steep on both sides, we just said that it was indeterminate at that point. It's kind of the same idea. We're saying that it's indeterminate here. You could technically kind of have either, which means we're not going to have either. All right, there's one other idea that I want to include in this video, and that is tangent lines at the poles. I think I'll provide a visual here of what I'm talking about. So let's just think of a coordinate plane. That's a little easier. But on this coordinate plane, I'm going to place a rose. And I'll just do a 3-petaled rose. Starting on the x-axis, so this has got to be a cosine rose, right? It would be, let's say it has a radius of 3. 3 cosine theta, right? Just practicing some of those facts. It will become important in the next lesson to be able to split this graph so like we can just look at like one petal at a time. We're going to start talking about areas soon. And in order to do that, you need to know these points of tangency that are cutting through the origin. Now, I didn't draw my petals very well, so they definitely look like they're touching more than once. They don't look like a point of tangents. But if this were sketched more precisely, the only point on the curve that they would be touching would be that at the pole. And then the diagonals would be kind of slicing through the petals to separate them from the entire graph or from the entire rows or whatever graph it is we're looking at. This would apply to other cardioids as well. I just like the way the rose looks best. So if they're going through the pole, it's going to be through 0, what we're going to need to know is what angle. So even though we're talking about tangent lines at the pole, we're not going to have to worry about the derivatives. We could examine that, but it's going to be simpler. All we have to do is let r of our function there equals 0, and then solve for those thetas to figure out where that's occurring. Okay, I forgot I wanted the calculator here, so I'm going to let that warm up while we start this problem. All right, determine the tangents at the pole for 2 sine theta cos theta. So this isn't one that we've talked about. You won't always be given a polar equation that you know something about, but you know that a lot of those same properties that we've discussed are still going to hold, and we're going to have access to our calculator. If I want to determine the tangents at the pole, I want to take the 2 sine theta cosine theta, and set it equal to 0 and solve this. Well, it's just as simple as knowing where sine is equal to 0 and cosine is equal to 0. Sine is equal to 0 at pi, just thinking in the interval 0 to 2 pi. Cosine would be at pi over 2 and 3 pi over 2. Now, because 0 and pi, right, their locations really make them the same line. We're thinking about theta equals, so you just need one of them. It's typically easiest to go with the smaller one. Same thing with pi over 2 and 3 pi over 2. Right, we can verify that. Okay, so that one I had the image, so let's maybe not put that one in the calculator, but let's do that for this one here. Determine the tangents at the pole for 3 cosine 2 theta. I guess I should have pointed out, just to emphasize, when we did that, right, we've got each petal now isolated. We know where to divide it off to get one petal at a time, what intervals on which to do so. All right, so let's do that for this last one. Determine the tangents at the pole for r equals 3 cosine 2 theta. I'm going to set that equal to 0. All right, so where is cosine equal to 0? Because this will just be 2 theta. That's happening at pi over 2. And I need to know, because I got to cut all these in half, so think of it as plus pi in, right? Since it will be happening every 180 degrees. Then we're dividing everything by 2. So it'll happen at pi over 4 plus pi over 2 in. And depending on what you're doing, you don't necessarily know how many of these that you would need, but let's see, what would our various angles be? Pi over 4 when n is 0, when n is 1, we'd have 3 pi over 4. When n is 2, then we'd be adding pi, so 5 pi over 4, and then 7 pi over 4. Now, thinking about the diagonals, these would be diagonal to each other, so that 5 pi over 4 is a repeat. Same thing with the 3 pi over 4 and 7 pi over 4 right there on the same diagonal. So more than likely, these are the only two that we're really going to need in order to divide out this function into its different petals. And let's look at this in the calculator, right? Just to remind ourselves that we can. I probably need to go back and change my mode. Let's see, I'm going to go to radians, and I'm going to go to polar, and then I'm going to enter this equation. So now I've got the r equals option, 3 cosine 2 theta. Do you remember what this one will look like? You know how many petals it's going to have? I'm going to, how about zoom standard? Let's see if that makes it. Yeah, there we go. Remember, the even powers double the amount of petals that you have. We've got a cosine function, so it's symmetric about the x-axis. And it does make sense that those diagonals, that those tangents at the pole are going to happen at pi over 4 and at 3 pi over 4. So I guess, I mean, really, if you've got that symmetry to work with, if you can look at the graph, the calculator, you can probably take an educated guess as to what those answers might be if you aren't wanting to solve it, right? Okay, the skills that we've developed today are going to help us tomorrow when we start looking at areas of these polar graphs. And so we'll be doing some integration to make that happen. And stay tuned to see all that.